Hi, my name is Jimmy Lee. In this talk, I will present our paper, Understanding a Program's Resiliency Through Error Propagation. And this work is a collaboration between the University of Utah and Lawrence Livermore National Lab. We are becoming more and more reliant on high-performance computation platforms for all kinds of scientific discoveries, such as weather and climate simulations, nuclear simulations, machine learning, and drug discoveries. And our passion for fast computation speed and large computation capacity motivate the industry to design machine with small computation units. This computation scaling has lasted for decades, but it's facing challenge now. As the size of computation unit shrinks in the chips and the number of components increase, the application run on those chips became more and more vulnerable to the errors, and the reliability of the result became challenged. And there are different kinds of errors that can challenge an application's output reliabilities. Errors such as truncation error, position error, and hardware errors are noticed by the domain for a long time, and they've been studied extensively. And soft error is special as it occurs randomly in any location at any time in the programs without notice or warnings. And software often are caused by like cosmetic particle hits on the chips or device noise in the environments. Those effects will switch the state of the transistor and lead to a single bit events during the computations. And the computation scaling threats, as we know, will make this problem worse in the future. There are many soft error corruption events which have been reported, such as like the Oak Ridge National Labs, the supercomputer Draga has a single bit events every 6 hours, and in Los Alamos, the Q cluster have like 26 errors per week. In the commercial applications, the Amazon S3 data center have reported a soft error corruption events, which end up with like in a data center, the servers start to sending each other like some log informations. So there are many techniques already exist that try to protect the program from soft error corruptions or like single bit events, such as like instruction duplications, component redundancy, and process duplications. However, if we want to use such technique to have a fully coverage protection for HPC applications, it will introduce like a significant overhead into the HPC platforms. And a more wise solution is protect the program component which is more vulnerable to soft error, as not every computation component is vulnerable to the soft errors. But this approach, the prerequisite is actually understand a program's resiliency and figure out the vulnerable components. So the classical approach that which is designed to understand a program's resiliency is through the fault injection campaign. What fault injection campaign do is usually try to deploy the bit flip models, which randomly flip a single bit of the programs during the computation, which to simulate the effect of the soft errors, and then observe the computation outcomes. This kind of like error testing usually result in like 3 different outcomes, such as mask, which the application run HPC system have a natural resiliency to the errors. So the error was being masked by the program logic, and at the end, the program generate an acceptable output. The other one is like the crash, which typically happen in the control of pointer variables, which cause some exceptions, or like a segmentation fault and ends up with a program crash. So the program can roll back to the previous checkpoints and rerun the application again. The worst case is the silent data corruptions, in which a single bit flip corrupt a program execution, and the error is being propagated around and introduce the error into the final output. And during that process, there's no warning and no notifications, and the final result is being used in a subsequent analysis or to make some critical decisions. Usually with these testings in the domains that it will end up with a ratio number called SDC ratio. And this number is basically the number of times we've been testing in these applications, which result in some data corruption, and the total number of times you've been testing. So usually the number which is smaller is better. This approach can actually have a pretty good understanding of a program's resiliency, but one drawback is the people need to repeatedly test one location, like different location one by one to identify those vulnerable components. And usually it ends up with like billions or trillions of like the fault injection testing. and it's not very flexible in many scenarios. So in this, in our research, we introduced a new concept called fault tolerance boundaries and fault tolerance threshold. Well, fault tolerance threshold is basically a value that in a single fault injection location, like the maximum value range, like can perturb to make sure that everything, the program will still generate an acceptable outcomes. And the fault tolerance boundary is basically give you all these kind of threshold values of all the fault injection set of applications. So before we get into more technical details, we kind of use these two plots to show the difference between those two different methodologies. So for fault injection, here is the x-axis is the dynamic instructions, and the y-axis is the inject errors, and left and right, they are the same programs. So for the fault injection campaigns, each circle here represent a single bit flips samples. So the campaign kind of deploy the multi-color simulation, random select certain amount of bits and flip it, and collect the for testing outcomes. And with that data, you kind of like give an approximation about a program's overall resiliency. In compiling the fault tolerance boundary was kind of like draw a line over the sample space. So basically everything below that boundaries, we will predict that going to be a SDC, a map mask, but everything above that boundary is going to be SDC. The advantage of this fault tolerance boundary, as you can tell from these figures, as it gives like each specific dynamic instructions a detailed information about the SDC ratio. In comparing the fault injection campaigns, there's many locations that you don't know what's the resiliency in that locations, as there's many samples are not being tested. Then the question is how we are able to get this kind of like fault tolerance boundaries. And simple approach is actually do the exhaustive testing, which you kind of basically every possible bit of a fault injection set, and to tell, and since each fault injection set have a limit number of bits to represent it. So for 32 floating points, you have a 32 different kind of bit flips happen here. As the testing is limited and the error you can introduce in this location through the bit flip is also limited. So we can find a threshold value which satisfies definitions. With this approach, we can construct a boundary and then predict the SDC ratio at each locations. So here we define a delta SDC, which is the ground truth SDC ratio in each dynamic instruction, compared with the SDC ratio predicted by the fault tolerance boundary we construct using this approach. Here's the three benchmark common HPC computation kernel. One is like conjugate gradient, FFT, and aerial decompositions. So under this comparisons, where we see is majority of the prediction compared to the ground truth is 0, which means the boundary make a perfect predictions. And there's a small portion of that actually kind of overestimate the SDC ratio if the value is negative. As we can see from this result, is like the fault tolerance boundary actually give you a pretty good analysis result compared to the fault injection campaign. Using this approach to construct the boundary is as expensive as like exhausting testing the applications. And it's not going to be flexible in many scenario tools. So the question is there any like more flexible way that we can, or cheaper way that we can build these boundaries? So here we introduce a assumption called error monotonic assumptions. It basically says like more error often cause like worse computation outcomes. So to explain these assumptions, what we can see from the point charts, like the x-axis is the dynamic instruction ID, the y-axis is the inject error you kind of introduce to the output of that dynamic instructions. So here you introduce the error in A, and then the error being propagated to other dynamic instructions, but the final output ends up with mask. In comparing the experiment 2, which the inject error was like slower compared to the experiment 1's propagation errors. And there's no errors in the previous dynamic instructions from A to E's. So here we infer that the experiment 2 also produces a masked outcome. The reason is that the error condition in experiment 1 is much worse than experiment 2. And also in experiment 2, the error was smaller than propagation errors in experiment 1. So with these assumptions, what we can do is we can collecting all the mask examples propagation data and use them to aggregate the propagation value in each dynamic instruction and take the maximum and use that to as the fault tolerance threshold value. And for all locations, we can use the mass propagation data to construct the boundaries with that information. We use like 1% sample of 3 benchmark to verify the performance of our approximation approach. So with the 1% samples, we construct a fault tolerance boundary and use that to predict the SDC ratio of each dynamic instructions and compare that with the golden ground truth SDC ratios. So what you can see from the first row, the x-axis is the dynamic instruction ID and y-axis is the SDC ratio of each dynamic instructions. And what we can see is like the early execution of the programs usually have like the worst prediction, but the later execution have much better predictions compared to the ground truths. To explain that why that happens, we can see the second row charts, the same with the x-axis, but the y-axis is the number of times error propagate through this location. So what we can see is basically the early execution has much less propagation frequency, but the later execution has much more propagation frequencies. So if we combine the information in first row and second row, you kind of understand that why the prediction quality in the early execution is much worse than the later executions. That's because like the later execution have much more propagation information to construct the boundary, but the early execution have very limited information for that. So the previous example, we show like 1% sample to approximate the boundaries and compare the results. And here we kind of show a full image of the relationship between the number of samples that used to approximate the boundary and the performance of the boundary predictions. And we use like 2 machine learning matrices, precision and the record. Usually you have a high precision and high recall. It indicates that your prediction is very good. So we use the 3 benchmark, conjugate gradient FFT and error decompositions. So over 3 benchmark, what we can see is the recall was increased exponentially at the very beginnings in all 3 benchmark. And when they close like 90%, things kind of getting 80 and 90%, things kind of getting slowed down there. In the error decomposition and fast response, the precision was close like 100%. But in the conjugate gradient benchmark, what we can see is that precision is kind of dropping down a little bit when you increase more sample. But as you keep sampling more data, this precision was kind of get back to 1 at the end. So in the first example, we show up that used 1% sample to construct the fault tolerance boundary, as like some location don't have enough propagation information to construct the fault tolerance boundaries. So it's gonna lead to like a poor prediction result. So to address these problems, we design a depth sampling method. In the classical fault injection campaign, the sampling is follow the uniform sampling process, which every location have a similar probability that will be selected as a samples. But in our cases, we kind of separate the sampling process into multiple time steps. But in the first 5 steps, we do the uniform samplings. And then with the first time steps propagation information, we construct the fault tolerance boundary and calculate the propagation frequency over different locations. So as we know, like the propagation frequency, some locations have a high propagation frequency, so we don't need to sample those locations, but some locations have much less propagation frequency. So we need more sample from that location to build a robust boundaries. So as we can show on the plots there, like the sample density and propagation density on below. This approach can repeatedly continue until there's a few mass sample left. So for example, in the next round, you samples, you probably sample like 95 or 99%, which outcome is masked. So you don't need to continue doing sample as you know that the boundary is kind of strong enough or like good enough to narrow to make the prediction for mass and SDC. For our examples, for the benchmark we've been selected with this adapt sampling approach, for conjugate gradients, what we see as the OSDC ratio going to be close to the ground truth. And the total number of samples that we need to understand that is like for CG, we only use like 1%. For area decomposition, we use like 5%. And for FFT, we use like the 10% at the end. This is overall prediction ratios. So this chart actually show you more detailed information over different dynamic instructions. So as you can see from all these three figures, the x-axis is the dynamic instruction, y-axis is the SDC ratio, and compared with the ground truth, they are kind of close to the ground truth with the SDC ratio in each dynamic instructions. One problem with this approach is that the monotonic assumption might not always be true, and which going to be ends up with a poor prediction results of the fault tolerance boundaries. But like during the approximation process, we only use the mass cases to approximate the fault tolerance boundary. The information of the SDC cases was not being used during the approximation process. So here we can use the SDC cases to filter the mass cases which does not qualify for the basic assumptions. And with that, it will improve the performance of the approximation. So if you see the first row, which is the previous experiment we showed before, the number of samples you use to approximate a boundary, the y-axis is the prediction accuracy. On the second row, you use the SAN approach, but you add the SDC cases as a filter to filter all the unqualified mass cases to use to approximate the boundaries. So as you can see here, in this case, the position here is almost close to 1 in all three benchmarks. And the recall is like growing exponentially in the early number of samples, but growing slowly and converge to 1 later on. One critical point of this approximation is that this approach can be verified during the construction process. So an easy approach that what you can do is you can choose 90% of the sample that you selected as the approximation samples that you kind of use that to build a fault tolerance boundary, and you can left with the 10% that used to verify how accurate your boundary can predict the vulnerability of different dynamic instructions. And this will give you a number about how much you should rely on the prediction of this boundary, whether you need to add in more sample to increase the prediction accuracy, or current boundary is good enough for you to understand a program's resiliency. So here we show an example of this verification process. So here we use the conjugate gradients, and it has 100 sample used to approximate the fault tolerance boundary with the different input, 20 by 20 matrices and 100 by 100 matrices. And the number of sample to build a fault tolerance boundary compared to the exotic campaign is 3 or 4 order of magnitude here. And as we can see, the final prediction result is close to the ground truth. And the position and the recall is both very high, especially recall with 100 samples, we can reach 96% recalls in this benchmark. And the uncertainty was close 98%. So here I will summarize our main contribution to end this talk. So in this study, we propose a new concept, fault tolerance boundary, and to understand a program's resiliency. And we propose an approach, an economy approach to approximate this boundary and use it to understand a program's resiliency. And at the end, we propose an approach that help user to verify the correctness of the approximations. Thank you.